it's also broadcast.
Right.
Okay. Well, okay. Hello, everybody. Thank you for coming. It's a great pleasure to have today Dr. Fieguth from University of Waterloo. As a full disclosure, of course, I met Paul when my first year of postdoc at MIT, and he was a graduate student. And Paul is a very lively person. He was then, and he still is, as you will soon find out. So Paul got his BA and BSc in electrical engineering from the University of Waterloo in '91, and his PhD from MIT in '95. And he joined the faculty of the University of Waterloo in '96, following a postdoc at the University of Toronto, if I remember.
That's right. Yep.
Yeah. And where he's currently department chair in systems design engineering. He's held several visiting positions, and the latest one at the University of Heidelberg in Germany, at INRIA in Sophia Antipolis, and Cambridge Lab in Boston and at Oxford University, and also the Rutherford Appleton Lab in England. His research interests have spanned many different areas, in particular statistical signal and image processing. There's a lot of remote sensing and imaging, in general, data fusion, and a lot of interdisciplinary applications. He takes a very, very hard problem, applies problems, and applies mathematics to them. He's also the author on in 2010 on the text statistical image processing and multidimensional modeling from Springer Verlag. It's a pleasure to have him here talk to us about some of his work on hierarchical modeling in imaging. Thank you for coming.
Great. Well, thank you, Hamid, for the kind of introduction and the invite. Like Hamid said, he and I go back quite a ways to about sort of early '90s when we were at MIT together. And I was here once before, quite some time ago, so it's nice to be back and to just have a chance to sort of see what's going on and sort of talk to you. So I have more material than I have time, so at some point I just have to stop. So I will be sort of going through the material relatively quickly with the idea more of sort of looking at the high-level ideas, because I don't think it helps anyone to sort of go through details of equations sort of, sitting in a group while eating a cookie. Your eyes glaze over. I don't think you'll absorb so much. And really, this work is not super old, but it's a few years old, but it has led to sort of more recent ideas, related ones, and I want to get to those more recent ones at the end of my talk. So anyways, so I've had a sort of lot of interest. One of my problems, I have too many interests. I think Hamid sort of along similar lines. And so I tend to sort of get pulled in a variety of directions. When it's time to sort of have a focused area, that's not such a good thing. When it's time to sort of have interesting things to work on, it's great. And so there was a group that formed at the University of Waterloo looking at what are known as porous media. I didn't know anything about porous media, but I was working with people in chemical engineering and physics and mechanical engineering, and that led to a lot of really interesting work where I sort of headed up the sort of data imaging and sort of spatial sort of modeling side of things. So outline is not so important. So porous medium. So I'm not going to talk about porous media a lot, but it turns out that they're pretty fascinating as far as sort of two-dimensional, three-dimensional problems go. And so, cement, bone, clay, rock, all of these things allow water to flow. It's just a question of how fast. And so there are pretty significant applications. So if you look at things like cement and rock, so then you've got construction, right? And things like bridges and the rebar rusting inside of bridges, how the water get there, and then the rust, pops the concrete off, et cetera. So pretty big infrastructure and construction implications. When we're talking about rock and sand and things like that, then you're talking groundwater and pollution, like from oil and like buried tanks and stuff, going in the groundwater and trying to understand how that flows. And then lastly, things like bone and cartilage, there's some pretty significant health implications. So it's actually an area that I knew very little about, but the more you dig at it, the more really significant applications come out. And it's pretty interesting. Now, how did I get related? So porous media, like this is carbonate rock. Porous media is unique in that it has structure, it's near-fractal, and so it has structure that spans 6 to 10 orders of magnitude. And there aren't a lot of problems in the world that are sort of fractal over that many scales. So this was actually constructed. This is tiny glass beads and then packed together and, I don't know, stuck in a furnace or something like that. But you get, in this case, not 6 orders of magnitude, but still, it's an 8,000 by 8,000 pixel image. It's pretty big. And so in this case, you have to put an epoxy and then slice it, look at it under a microscope. This is my favorite one. In that you have really unusual sort of structure. We've got sort of these patchy areas. We have large voids and solids. So it's fairly heterogeneous, kind of spatially non-stationary kind of thing going on. And the question is, how can we work with that? Now, you could ask, well, why do I want to work with that? Obviously, we've got microscopic images. Isn't that good enough? And the key issue is the following. If I want to study porous media in 3D, first of all, I have no way of imaging them in 3D at that kind of resolution. These were all 2D in a microscope. I can't do that in 3D. So that's problem number one. And MRI does not give me any kind of resolution anywhere near that. Okay, MRI is about 2 or 3 orders of magnitude back from this resolution. And number three is the key thing that we want to study in porous media is how water flows through the medium. Okay? And you can't do that in 2D. You have to do it in 3D. So the people who study this need large three-dimensional data sets. Okay, so given that you must have large three-dimensional data sets and you cannot acquire them by measurement, it means you have to acquire them by simulation. Okay, so enter the image processing kind of people like me, who are then called upon to come up with, 1,000 by 1,000 by 1,000 cubes of a porous medium that looks like that, please. Okay, so there we go. And so they want to do Monte Carlo testing, so they need lots of samples, not just one. Okay. So there are, of course, strategies for, doing synthesis of random things. I don't know whether you've studied random fields at all, but if you've had even a sort of a high-level sort of statistical spatial statistics course, or if you haven't, read my book, as Hamid sort of mentioned. It's a great book. I'm teaching from it this term. So Gauss Markov random field, you can use FFT methods to generate huge random fields. Of course, they're continuous state, so I can discretize them. I get a binary thing. The problem is it's terribly hard to control what that binary thing does because my model is actually a Gauss Markov random field model for the continuous state process. Once I binarize it, I actually don't really have a good sort of sense of what that binary state is doing. Ballistic methods is a whole area basically where I say, oh, you want blobs? We'll just create physics, and we'll throw blobs in the image, and we'll try to keep the blobs from touching. It ends up being a very, very sort of badly constrained optimization problem where we're trying to simulate physics, like shaking balls in a cup or something like that. It is computationally terribly difficult to actually get to converge to anything meaningful. And so the last one would be something like simulated annealing. I would hope that at least a lot of you have heard of it. It's basically a discrete state sort of optimization process by which we slowly sort of anneal a random field to sort of converge to something. Problem is, it's typically very slow. All right, so given these, it's the last that in principle allows us to work with the kinds of models we're interested in. It's just much too slow. Well, that's kind of problems that sort of interest us. So a Gibbs model, let's ignore like a lot of the details. Basically, H, there's some kind of criterion. So if H, I want to do energy minimization. So if H is big, the field is bad, and if H is small, the field is good, okay? And so here is kind of the detail from the porous media sort of side of things. It's not so important. The point is basically I have some kind of target which I'll measure, I guess on the next slide, via chord length. So this is standard, not in image processing, it's standard in porous media. So basically I'm measuring how long a series of white pixels do I have, how long a series of black pixels do I have, and in the vertical and horizontal direction. And then, so basically that expression at the bottom there says, just penalize the overall inconsistency between the distribution of sort of observed chord length patterns as opposed to modeled ones. Okay, so this is just a detail. I could do other models. I could do correlations. I could do like spatial size of blobs. It doesn't really matter. Okay, it does essentially any model you would propose, you would run into. I'm getting ahead of myself, but that's okay. You would run into this kind of problem, or even worse, that. Okay, so it doesn't really matter whether it's a chord length or a correlation model or a 2D blob model. Simulated annealing has enormous difficulties converging, and so literally after 3 days of running it, you haven't gotten even remotely close to something that looks like your original model. Okay? So it's just backing up very briefly. So we had been here. So basically, a Gibbs sampler is just randomly sampling at each location from the conditional distribution. And so if I'm going quickly, this is easy stuff to look up because this is not really the point of the talk. But so that's a Gibbs sampler. And then annealing basically does Gibbs sampling while we slowly lower a temperature such that we converge to the global optimum. All right. So that's all well documented. You can read that up on Wikipedia. And so the challenge here has to do with what's known as an energy barrier. That is, if I start off with a random domain, you see the blobs over on the left there, they want to be relatively large. And so simulated annealing tries to do that, but once it starts creating sort of, let's say, small-sized blobs, the energy function on the left says, I don't have any small-sized blobs, I don't like the look of this. And so it creates a barrier from getting from here to there. Okay? And so energy barriers are commonly talked about in physics, but they're terribly common in any kind of energy minimization scheme, because I don't know how to get from A to B without crossing this barrier. Does that make sense? Okay? So the problem is, though, that my model, in fact, doesn't want little blobs, and so I can't get around that fact. All right. So the point is we have clear scale dependence, and somehow we have to introduce an explicit notion of scale rather than just throwing a model at the problem and hoping that it converges. All right. So this is one of my favorite examples. It's a little bit of a distraction. People familiar with the Ising model, or Ising, if you're pronouncing it right? It's basically just a model where each pixel interacts with its 4 neighbors. Okay? And it's a binary model up, down, and it models a ferromagnet. So a magnet can, north could be this way or that way. Obviously a gross oversimplification, but it was classically in physics the first model, or spatial statistical model, to be analyzed in complete closed form analytically, and so it's sort of famous for that reason. So what I'm showing here is a tiny bit complicated, but it's actually not that bad. Bottom left is the actual binary field. Okay? And so here, the number at the top there, coupling of 0.1, so that basically says how coupled these pixels are, so 0.1 means not very much. So basically, I just have random stuff going on. Okay? And so we see that in the bottom left. And then as I move towards bottom middle, bottom right, I'm just averaging the field more and more, and that's why it just becomes kind of this bland green, because if I take random noise and start averaging it at coarser scales, I just get zero mean. Okay, so that's what we're seeing. The middle part is a tiny bit complicated. It's just showing the state as a function of scale. So at the finest scale, I only have binary states. So you see green top and bottom and nothing in between. That's because when I have a binary state of -1 and 1, there are no values in between. And as I go up to coarser scales, you can see intermediate values filling in. And eventually, at a sufficiently coarse scale, everything is zero mean, and so all the energy is focused there. So it's like a two-dimensional histogram with color showing the prevalence. So as I increase the coupling, you can see a couple of things happening, which is that the blobs in the bottom left are getting bigger, and so therefore, I'm starting to acquire structure on coarser scales that you can see in the bottom right. And you can see my statistics moving over in that my field requires coarser and coarser scales to revert back to zero mean. Okay? Now, something remarkable happens right around 0.441. So here I'm still in that same domain of behavior, just my blobs are getting larger and larger. And if I go from 0.44 to just a tiny bit bigger, I get a spontaneous bifurcation or phase shift or phase change. And this is like phase change, like from liquid water to gas. It's physically exactly the analog. And so what's happened here is I've gone from basically random islands, larger and larger, to here, the Pacific Ocean with small islands in it. So here there is a preferred magnetization out to infinity. Here, there is no preferred magnetization. If I go to a sufficiently large scale, I go to zero mean. Now, if you look in the bottom left, the random field doesn't look so different. I mean, obviously, one's got a red background, the other one's got a blue background. But at the finest scale, these two are close to indistinguishable. The difference, the really striking difference between those two appears at the coarse scales. Okay, that doesn't sound so profound. But the point is that large-scale effects manifest themselves often very weakly at the finest scale. Now, binary random fields aren't so exciting, so a lot of you might think, okay, I see that, but not that impressive. All right, well, let's try something else. Suppose I synthesize two Gauss Markov random field models. The value in parentheses is the correlation length. So the left one there, F1, is a slowly varying kind of random field, and the one on the right, F2, is a rapidly varying random field. Okay? So I've got two random fields. Everyone okay with that? And then at the bottom, I just do a little trick there to make it binary. So I'll take the sign of both of them and then take the max. And so that gives me something like this. So basically, I see large-scale structure, the white and the non-white part, and I see fine-scale structure, like kind of the finer texture. Okay. And so I can try to plot like a chord length distribution. It shows me nothing. That's because a lot of the chords are quite rare. So I'll look at a log plot. So, all right, whatever. I got some distribution. Okay, so let me compare these two. So the one is clearly single scale, and the other one has large scale structure. When I compare those two distributions, obviously at sufficiently long chord lengths, I see a difference. But note on the vertical scale, it's down about 2 to 3 orders of magnitude in terms of the size in the histogram. So if I had asserted this as a histogram and said, please match it, these two would look pretty close to each other, even though to our eyes, they're strikingly different. So one step more subtle is I'll do the same idea as before, but I'm going to bias it. That is, I have two random fields, but one is going to be biased just a wee bit shy of 50-50, and the other one's going to be biased just a little bit ahead of 50-50. So it looks like this. So you see the left field, the random part is a little bit more blue than red, and the right one has a little bit more red than blue. Okay, not a big deal. Now, if I coarsify this, nothing happens much initially. Then obviously what's going to happen is the one that had more red than blue, as I take majority voting, all the blue disappears. And the other one that had more blue than red, as I do majority voting, the blue sort of maintains itself. And so I see at a coarse scale a huge difference between these two, just because of that bias manifesting itself. Of course, I have a nonlinear step because a majority vote is not just a linear sort of operation. But nevertheless, pretty different. If I look at the chord lengths, they're indistinguishable. So this is getting a little bit weird. So something which is strikingly different at a coarse scale, and that is even obviously different to our eyes, manifests itself almost not at all in a model that's typically used in porous media for distinguishing between different kinds of distributions. All right, so there we go. So large-scale effects tend to really not appear at the finest scale. And so in other words, if you want to have if you want to be able to represent this kind of phenomenon, you're going to have explicit scale dependence in your model. All right, I'll come back to that momentarily. So how do we do hierarchical models? Well, if you've ever sort of studied like wavelets or multi-grid methods or things like that, you know how that works. I have a coarse scale thing, and I project it to finer scale, and I perturb it a little bit. I nudge it a little bit. I add a little bit of shift here or there. Okay? Problem is, for discrete state things, that doesn't work. Because in continuous state, I can take something, I can shift it a little bit. In discrete state, it's either there or there. There's no perturbation. There's no nudging. I have to either take it from there and leave it there, or I have to put it down there. So hierarchies don't really live naturally in discrete state world because I have no ability to take a coarse scale thing and slightly adjust it. Okay? I hope that makes sense. So that's why there's been work for 30, 40 years on sort of continuous state hierarchies, but in discrete state world, it's been much, much, much harder to make progress. And yet we have all kinds of discrete state random fields, like if I have classes in a remote sensing problem between, say, agricultural land, urban, and forested. Excuse me, if I have like a labeling problem in human anatomy between, like, this is the heart and this is not the heart, or here are the bones and here are not the bones. Any kind of labeling problem is discrete state. And I have loads of labeling problems that I'd like to represent at on a hierarchy or sort of non-locally. It's very hard to do. Okay? And finally, hierarchies also kind of live in sort of like blocks, and most problems are not well represented as piecewise constant squares. All right. So in principle, mathematically, we can do this. So the classic paper by Gibbs, by now from many years ago, is from '89, where it showed that if I want to talk about a random field on a fine scale, there exists a definition of what that field looks like on a coarser scale. Problem is, A, it's really complicated. B, if I have something that's Markov, when I downsample it, it is no longer Markov. And so what used to be a local model has now become a non-local model. So that's a big drag. Okay? And that's the kind of the two-sentence reason why no one does this. But in principle, mathematically, it's not a problem. The problem is I don't know how to do the modeling. Okay, so we move on. So I could, of course, assert a model at each scale. So that's not hard. I can, in principle, learn a model at each scale. The problem is, how do I couple the model across scales? How do I make them interrelate? So I can either do implicitly or explicitly. So implicitly is most obvious. I had a student working on this. It is terribly hard. Basically, what I do is I run a model at a scale, and I initialize the next scale based on where the previous scale got to. Very intuitive, makes good sense. It doesn't work. Why? Because how do I ensure that the structures that were introduced at a coarse scale are not distorted or eroded or removed at a finer scale? And if you've ever done any annealing, you know that you start annealing at a high temperature where you basically randomize everything. Well, you can't do that. If you randomize everything at a finer scale, you've thrown away everything the coarser scales did. It doesn't work. Okay? We spent a long time finding out that it doesn't work. So that's more or less what I just said. So instead, you need some kind of explicit coupling. That is, I have a random field at each scale, and I have to somehow couple these and constrain them. And so I have to basically introduce a ternary model so that I have some notion of what's constrained, black, constrained, white, and something in between that is unconstrained. Okay, so we don't need to see the equation. So if I have a full image and then take an excerpt of that, in principle, I can downsample that over scales, where I'm now, rather than taking majority vote, I basically just say, was everything black, everything white, or was it a mix? And so that gives me a model as a function of scale, which in principle I can learn at each scale and then reproduce. Okay, and so we can see things like, for example, obviously if I have large structure, then the characteristic scale at which that gets seeded or becomes ambiguous is different from having small structure. That's pretty obvious. But there are a couple of key benefits here in doing a sort of explicitly coupled model. Number one is a finer scale cannot undo what the coarser scale did because the coarser scale structure doesn't change. Number two is I am welcome to have a crazy temperature schedule at finer scales and go crazy random, because no matter how random I go, I can only randomize those things that the coarser scale didn't constrain. So I think I've talked about that. And so just a couple of illustrations, but let's get, so the benefits in computation are that I now only have actually a small fraction of the overall sort of image that actually needs simulating. And so when you have an 8,000 by 8,000 image, that makes a big difference. So for example, here are the raw number of pixels that I have to sort of work on as a function of scale. So it still increases. My finer scales are harder, but the fraction of pixels I have to work on is decreasing rapidly. That is, the coarse scales really do solve a large fraction of the problem, so that by the end I'm working on, say, 2 to 5% of the problem rather than 100%. And so that's a speed up of 50 to 80 times, or 20 to 50 times. And that ignores the whole issue of energy barrier, which I solve by having the problem attacked at the coarse scale. Okay, so I think I've talked about that. So let's take a look. I mean, what we want to see is whether it actually behaves or not. So here's some training data. And so we can just run down and scale, and we see sort of structure being introduced. Everything that's gray is not yet constrained, and eventually gray just becomes a boundary that I can sort of constrain until I arrive at the finest scale. So that's interesting. We don't have any energy barriers because any large-scale structure that needed creating got created at a coarse structure, at a coarse scale, where there was no barrier. So basically, at whatever scale I need to introduce individual pixels, I can do that. Okay? The problem is if I want to create something large that requires many pixels to be flipped, I can't do that at the finest scale. But here it's free, so to speak. Okay? All right, so does it work? So here we go. So if I train, on kind of a local blob model, after a few minutes, I get kind of the left image. After a few days, I'm stuck with the right one. And that's due to two factors. The left one has a speed up of approximately a factor of 20 due to the fact that I've constrained most of the pixels, and another factor of 1,000 due to the absence of an energy barrier. Okay? And so here's just a few examples. Input in the left, output in the right. It's not obviously perfect, but it's awfully good. This was the first example that sort of convinced us that there was pretty strong promise, because the collaborator, who's a chemical engineer in Porous Media, couldn't tell which one was fake and which one was real. And once they can't tell which one's fake and which one's real, you're probably getting pretty close to synthesizing the kinds of things that are worth analyzing. Okay? Carbonate rock, again, fake and real. Okay? And so where to from here? And so I'm right on time, because I'm going to have time then to talk about sort of more recent things a little bit more calmly. So once I've done 2D work like that, there are 3 obvious extensions. I could do it in 3D. I could do it multi-layer, so having like a hidden Markov model. Or I could do it posterior, meaning that I introduce measurements. Okay? So in 3D, we haven't yet done. We know how to formulate it, but there's an awful lot of data structures and search trees and things like that that come in that we haven't yet done and that we would need to. Hidden fields is in principle straightforward. I just introduce more than one random field and define some interaction between them, and it lets you do sort of fun things like this, where I can have a single model that is dependent on a hidden layer, and that can give you what looks like sort of interesting sort of semi-continuous behavior at a fine scale. The most impressive one, though, has been posterior. So again, I don't know how much background you have in sort of statistics, but if I have an energy model as a function of an unknown x, that's essentially a prior model. If I introduce a measurement, m, now I have a posterior model, because that model is constrained on these measurements just showing up. And so in principle now I can do estimation based on measurements. And so I get something like this, which is pretty remarkable. But indeed, the measurements there in the middle are scaled for what you would typically get from an MRI. And so that in principle, this would be the kinds of measurements you're getting in 3D. And indeed, the reconstruction on the right is nothing more than simulated annealing. Obviously, I need a good model, but the model did not overfit and memorize the structure on the left. The model was learned from a much, much larger image, but is enough to constrain the behavior that we're seeing here. And this was sort of that funky, sort of unusual, sort of multi-phase kind of image. In this case, our measurements are a little bit more complex. I don't want to get into it. But there's some pretty promising ways of moving forward once you're able to do sort of modeling in a Gibbs framework, but where you have scale dependence that allows you to get past energy barriers. All right, so that gives us a background of what interests me and my group in sort of hierarchical, sort of discrete state things. So now I want to just, these are much shorter, but I want to just talk briefly then on, there we go, sort of some much more recent work. These are now, this short talk and the other short talk are PhD students of mine at Waterloo right now. And the kind of things that we're doing in terms of sort of graphical models and hierarchies in the current context. So this student is interested in, again, large-scale sort of modeling and relationships. And so the example I had before, like this icing model, the icing model is very trivial. I mean, it's not trivial if you're doing analytical work, but on a computer simulation, it's a pretty bad model of reality. Almost nothing looks like an icing model. So really, you need a more non-local model, that is a model that has many more interactions. Okay, so that's fine. And so I mean, this is just background on graphical models. You will know much of that. I mean, we use graphical models in speech. We use them in image processing. That's fine. So we know that the complexity increases as a function of how many interactions I have. That would be true regardless of whether it's a random field or some kind of other optimization problem. The larger your kernel, the larger the number of connections, the larger your network, the more parameters you have, the more difficult the learning is and the actual sort of both training and running. The problem is if you have a local model, then you get all kinds of artifacts and strange things happen because the model just lacks context. Okay? And so in this case, the segmentation is poor. But if I had a non-local, in this case, I believe it's conditional random fields, or CRF, but it doesn't actually matter exactly what kind of model it is. But the more non-local the model, the more both degrees of freedom are encoded into the model, and the more the model can understand the surrounding context. Now, there's some interest in what are now called fully connected graphs. That seems kind of extreme, but nevertheless, people are working on that. But the problem is that in general, they're not tractable. So they're kind of theoretically interesting, but you're not likely to actually want to sort of do those in practice. So the obvious question is, well, why do I want all connectivities? So I know that local is a problem because it just doesn't keep track of things. Global is also a problem. So ideally, I'd like, as it says here, only the informative ones. But basically what I want is a stochastic model. I want some kind of, this is now not even a stochastic random field, is that the model itself is stochastically driven. Okay? So, I mean, this kind of thing is not new to us. There are people who've worked on random graphs for a long time. There's all kinds of things. I mean, there's a lot of work on scale-free models and models of society and internet and things like that. So network theory is super active area these days. And so this touches sort of on that, except we don't really need sort of the subtle connectivity properties of graphs because we're going to assume that we have enough connections that our graph is not fully connected, but is not partitioned. In other words, every node is connected to every other node. If you're talking things like the internet and robustness to like a server failing, then you're worried about, will the internet sort of fail to have connectivity? But in those scale-free networks, they tend to be much, much less connected. We have a much higher degree of connectivity. And so I guess all I'm saying is we're in a different part of the random graph domain than people who study critical infrastructure and things like that. Nevertheless, there's a lot of interesting and related work that goes on there. So yeah, we can have nodes connected to other nodes based on some probability. But of course, we don't want to do it at random. So we want to have some kind of metric or some kind of rationale for what makes a node worth connecting to another node. And so in this kind of trivial example, I guess we could do it based on color and, say, spatial statistical characteristics. But you could define other metrics. Okay? So the key is more the overall premise that it is perfectly reasonable to propose non-local statistically connected graphs based on some metric. And then the question is, what degree of benefit does that give you? Okay? So anyway, so that's more or less what I was just talking about, which is we start off with a fully connected thing or an image. We identify all these probabilities, and then we essentially do sort of random sampling from that distribution. All right. So a typical kind of example. So here we have sort of on the left image. Then in this case, it's manually seeded just for illustration purposes. So the dense local CRF, again, it's conditional random field. So it's a random field model, but it is dense, but not fully connected. We have to be careful of our wording. So it is local. The model on the right has around the same computational complexity, but is not local. Obviously, that means I have fewer local connections, but I've added additional non-local ones. So that total computational complexity is left effectively unchanged, but I'm taking advantage of those connections that actually matter a lot more. Obviously, the complexity is a lot less than if I were to try to have a fully connected graph, which I don't think we could even solve for this kind of problem. Okay? And just one other illustration. And so you can see, typically, there's a lot more segmentation failures and sort of funny little bias effects in local models than in non-local ones, because the non-local ones, just plain and simple, have a lot more context to absorb. So then the interest is, can I move this from a single plane model, like a conditional random field or a Markov random field, to a multi-plane model? So I know everyone and his dog is doing sort of deep networks. And if you buy a fast enough computer, then you too can publish papers. But it's still an interesting question, given that one is doing these gigantic networks, whether the same principle couldn't apply here. That is, one of the huge, let's say, drawbacks of at least what I see in sort of deep learning, and sort of my main motivation for this work is it just feels wrong to need 50 million training samples to train a network. Okay? And clearly the reason, in the context of this talk at least, why we need 50 million is because the networks are densely connected, they're fully connected, and there's just plain too many parameters. So, what's that? They don't mind, right, but I mind. But I think it's an interesting question. To what extent can we do parameter reduction so that more modest problems with fewer sort of training samples could in principle be robustly learned? And so there's at least two ways of tackling this problem, or two ways to look at the problem, and we're trying both. One is, if I have a fully trained model from the 50 million data points, as I prune connections out of this model, how far can I prune before performance really gets affected? That's one way of stating the problem. The other way of stating the problem is, I'm going to start off with a sparse problem to begin with. Can I reliably train the sparse problem? And do I know a priori how to define that sparsity? In some ways, that's trickier. If I start with a fully trained network and pull away weights that are really tiny, that's sort of easier, but it requires me to get that big network in the first place. If I have limited training data, or if I have limited computational power, then I can't actually train that thing. But those are the two sort of interesting perspectives that we're working on. And I mean, this is kind of as of last week. So this is where we're at right now. I find that fascinating because there's something that, like I said, I find really unappealing about gigantic, enormous training sort of problems. And most of pattern rec does not need to work that way. And so can we constrain the problem? So anyways, so we're looking at convolutional neural networks. If you're not familiar with them, again, it's easy to read up on them, but I have a small convolutional kernel, and that moves over the image, and that kind of describes how I go from layer to layer. And this image is a little bit hard to see. If you look carefully, you'll see that the kernels are not dense. That is, they're kind of, we should have shaded the grid to make it more obvious. But there are pixels missing. Okay, so the idea is that my convolutional kernel is now sparse. But it is bigger, so spatially. So is there any benefit to be had as I make this larger and larger and sparser and sparser? And of course, in the extreme limit, I start losing so much information of my central point that it does not help. And so there's somewhere there's a happy medium in between, and that's what interests us right now. And so here's a very, very recent result, just kind of as an example. So in this case, I take a fully trained network and I start cutting back. And you can see that I can cut back almost half the connections before the performance really is materially affected. So that's fascinating. And it's a factor of 2 right there for free. I haven't yet fully answered the questions that I articulated earlier, but this one plot here suggests there's lots more to think about. Okay? And so probably, I would like to think if we look at the problem in a slightly more nuanced way, we can probably do yet a fair bit better than 50%. Okay? So, and it also remains to be seen whether these little fluctuations are statistically significant or not. We just need to plain do a lot more training runs. So we can talk about that in a couple of minutes yet if you have questions. So the other bit that I wanted to look at, and something's going crazy here, so I don't know why. Good, it settled down. So just one final sort of thing that we want to look at. So in this case, not so much sparsity, but now an explicit notion of scale. So you're seeing my bias as a supervisor coming in. So I've got 2 students who are interested in sort of deep networks. And I'm saying, well, I'm not really a deep networks guy, but I like stochastics, and I like random fields, and I like scale-dependent things. So you can see where sort of students' research then heads off. So this student is looking at questions of scale. And so the other thing that irked me in deep learning is that I got all these filters, but I don't really know what these filters are doing. And so I've got multiple layers in my network, but what are these layers doing? Now I realize that papers have been written trying to understand effectively the kinds of filters that are being deduced as a function of scale and trying to attribute, these are more sort of fine scale texture-like and these are more sort of non-local-like. But I'm personally not yet really satisfied that that clarifies for me what's actually going on. And probably to some extent, we can't actually say what's going on. It's a huge, vast network that's just trying to solve an optimization problem. So for me, coming from a sort of a scale-dependent and a multi-scale kind of perspective, it's something I want to look at. So, all right, a single neighborhood, a single scale gets a single level of detail. Okay, and so we know that. But there's lots of work that's been done on scale-dependent things, and I mean, Hamid knows where some of this is coming from, because where I did my PhD, that's what we did, was sort of scale-dependent stuff. And so it's sometimes embarrassing talking to people who have known me from back then, because they're thinking, like, really? You haven't changed like your research area in 25 years? You're still stuck in the same rut? But it's not quite the same rut. I was in a different rut when I was doing my PhD. So I'd like to think that I've moved on a little bit. So I've become a little bit more open-minded. Anyways, here's at least 3 kinds of common scale-dependent representations. So the probably oldest is a pyramid representations coming out of the 80s, wavelets out of the 90s, and the sort of scale space, late 90s, early 2000s. All of these attempt to look at an image as a function of scale in some way. Fine, fair enough. So the point is, what I'm trying to say is that this is not new. I'm not inventing it. And recent work on deep learning could probably benefit from some of this. All right, let's think about that. So I could look at an object at multiple scales, i.e. multiple resolutions, or multiple scale spaces. And so ideally a nonlinear scale space, like linear scale spaces are basically just blurring. So there's not much there, okay? Like, so we can more or less leave that. But nonlinear, so anisotropic diffusion scale spaces tend to blur out fine scale details and preserve coarse scale structure. That's kind of interesting. Maybe my deep learning should know about that explicitly rather than implicitly. That's where I'm going. That's kind of the high-level message here. Everything else is detail. And so the hypothesis is, well, to some extent, the fine scale is giving you things like appearance and texture, whereas the coarse scale explicitly, rather than hoping that the network does it, the coarse scale in a scale space representation gives me things like shape. Okay, texture's gone, but shape is there. All right, so there's at least 3 architectures that I could propose here. All right, and we're still not sure which one's the right idea, but there's at least 3 ways to go. And if you have questions or if you have opinions, I'd be certainly happy to hear it. So in principle here then, I have to remind myself exactly which one we're looking at. So here I'm explicitly inputting different scales, like from a scale space method, into a network, so that the network has that as input. So I don't have to rely on the network to find the coarse scale stuff. I'm giving it the coarse scale stuff. Okay? And so the business off to the right is just, I have a pooling layer P, blah, blah, blah. That's kind of the standard stuff that people do in deep learning. If you're not familiar with it, you're not missing anything. If you are familiar with it, we're doing the usual kind of thing. Okay? So we're as much as possible trying to stick with the same standard framework, and then augment it in some way, in a deliberate way, giving it sort of the information at a coarse scale and fine scale that we think would be relevant. So that's one framework. Another framework is maybe I should explicitly be downsampling so that I'm not relying on further layers to be aggregating things from a fine scale, but rather I'm going to give a small local filter this coarse scale information. Okay, could do that. And a third possibility is now I'm changing my pooling. So what I'm doing, my filters are all the same size, but the nature of the pooling layer, how I'm grouping or aggregating things after applying filters is different. All right, so we don't yet know exactly where this is going, but the point is there's a variety of ways of trying to assert scale-dependent structure in doing training, learning in these kinds of architectures. And so again, this is very, very recent. Just giving a quick sample of the kinds of results that we're seeing. And so here, just trying to remind myself which line is which. So, I mean, the standard is the purple line. That's the lowest. So that's good. So basically, all 3 of these architectures have something to offer. But the most promising ones are where I have either multi-neighborhoods or sort of multi-neighborhood pooling, the green and red lines at the top. And I mean, the shift is not gigantic, although in kind of this kind of deep learning, again, when you're getting bits of a percent, they keep adding up, and people like that. But in some ways, what I find more interesting is a factor of 3 in reduction in the number of filters that you need for the same performance. Again, going back to the previous mini talk that I showed you, which is I can reduce the degrees of freedom by factor of 3 and maintain the same performance by explicitly pulling out that scale-dependent structure and making it available rather than trying the network to find it implicitly. All right. And I don't think basically same ideas. We're just looking at performance as a function of noise and similar kinds of things, which is that clearly, particularly anisotropic diffusion has a nonlinear step in it, and so does a lot of noise rejection. And so you're going to tend to get a lot of sort of improvement in sort of relative to noise as opposed to the purple curve, which is the standard sort of approach. There we go, and that's it. So I've probably covered a little bit too much ground, but hopefully give you some stuff to think about. But basically, the high-level message is I have a lot of interest in how I sort of work with scale and sort of statistical structures. The porous media example is relatively mature, but I find a lot of fun because it's what you neat things that you can do with simple local models like an icing model and get, in my opinion, pretty deep insights in terms of behavior and the statistics. And then 2 really recent applications in graphs and scale that hopefully resonates for some of you because it connects to where a lot of the interest is at these days in machine learning and image processing. All right, thank you.
for some questions?
Yeah, I could have talked 5% slower and still been in time.
Any questions? Yes.
Go ahead.
So you mentioned you were looking at pruning weights in deep networks. How are you going about doing that?
Right. That's a good question. I mean, and like I said, I talked with a student last week about this. It's very current. So, I mean, the most obvious two strategies just to sort of start exploring this question would be either random pruning, which of course would be stupid, but as a baseline comparison, you'd like to do that because that would be like learning into a sort of a random network. And the other would be pruning the smallest weights, closest to zero. The problem is that close to zero alone doesn't really guarantee things because if a signal coming into that small weight is very large, the overall impact is like a small signal going into a rather large weight, right? And so there are definitely nuances there. And there's almost certainly cross-dependencies that removing this one weight could very well be related to whether another weight is removed or not. So we haven't gotten very much beyond that. So right now, we're looking, and then if you're familiar with this kind of thing, we typically have a few convolutional layers, which basically learn the features, and then we have a classifying layer at the end. And so these two behave very differently. The convolutional are small kernels, and the classifier layers are densely connected networks. So these two behave as very different animals, and so the question is also, are there strategic reasons for pruning weights preferentially or differently in these two domains? And that's the question we articulated last week, and I don't yet know the answer. But that's kind of where our thinking is at. But these kinds of simple results, or the initial results there, are based on pruning closer to zero. That's a good question, and that's exactly what we're trying to figure out.
Sort of guarantee on performance if you use the multi-scale model to prune the weights?
Well, I don't know what that would mean to use a multi-scale model. I mean, my graph model already has multiple layers. Of course, that's very different from multi-scale, right? So here I explicitly had notions of scale, like image resolution coming in, whereas in the deep learning, I've got multiple layers, but I don't actually know that I have concepts of scale going on. So I don't know how I would use a multi-scale model there. Maybe what you're saying, sort of the converse for us is, what would, rather than taking a dense model and pruning it, what would the sparse model look like in the first place? And which sparse synapses or connections, when they're included, lead to much superior training as opposed to not? We don't yet know the answer to that, because I just don't know how to formulate that problem. But it's certainly the problem that needs formulating, because really what we want to do is we want to start off with a sparse structure. We don't want to start off with a dense one and prune it down. That's kind of like beating on the hammer in a sort of crude fashion. It'd be far more elegant to learn the sparse one. But how do you know a priori what weights you want? Well, maybe that's the wrong question. Maybe by starting with the correct sparse structure, those weights which you permit are the ones that the trainer then learns to use effectively. So that there isn't a magically correct sparse structure, but there are probably ones that are better and worse. So that's where our thinking is at right now. And if you have further thoughts on that, I'd be interested to hear. But anyways, I find that whole sort of domain of thought fascinating, because it's basically how do I reduce the degrees of freedom to do robust learning, right?
Question. Lee, yes.
Hello.
I'm thinking regarding hierarchical modeling.
Yeah.
In some cases, I'm not sure how to handle that. The scale could be different. For example, image data, the scale could be 100 to 1 pixel, maybe 100 meter.
Right.
Then at the ground level, we may have finer. Then that may require different information.
Right.
Right?
Yes, absolutely.
I'm saying another case is that people talk about brain imaging.
Yep.
Sometimes you brain at the cell level. Sometimes you have total brain level.
Right.
Is that a way to this extreme scale?
Right. Right. Well, I mean, certainly the porous media were extreme in terms of scale, but they were much more homogeneous in terms of, I guess, nature. Like at the brain, like the hippocampus, as opposed to a neuron. Like those two are just like night and day different in terms of structure and shape and so forth. So, if I understand you correctly, Yeah, I would say right now not, and partly it's because the scale-to-scale transformation, or if you will, the scale mapping that I'm using here are well, here I have to be careful. So in the deep learning, we're learning filters between scales, and so we don't really know what we're doing. In the earlier sort of porous media work that I showed, there I have asserted basically kind of a majority wins kind of scale, which makes sense when I'm talking about molecules which aggregate to become stone, but does not necessarily make sense when I'm talking about cells aggregating to become like a more complex structure. So I almost think that for that kind of case, I need to articulate, it's almost like a forward and inverse model. I need to have a more subtle transformation between scales because my definition of fine scale and coarse scale is not just a matter of resolution, it's a matter of sort of structure. That's right, that's right. So that's hard, but it's interesting because, I mean, I like inverse problems. That's the kind of thing I find intriguing. And so having a sort of a non-trivial sort of upward and downward model between these sort of different scales. I've done a little bit of work in that area, but really only for linear kinds of problems, where we know that the upwards and downwards transformation, they have to be pseudo-inverses of each other to sort of define a proper, I mean, that would take a little bit of time to define. But basically, if I want to have an interpolation and a subsampling operator that are a complementary pair that don't progressively corrupt more and more if I sort of go back and forth, they have to be a pseudo-inverse pair. But that only makes sense in the linear world. Something like the brain is not going to be a pseudo-inverse pair. It's going to be some more abstract kind of transformation. I don't really know what that looks like, but I think it's a great question. And it's probably worth thinking about. And we're getting to that point. Like there's a group that I visited in Germany, and they're trying to actually do three-dimensional segmentation of neural structures. Now, not human brain, but they're like looking at, I don't know, insects or, frog or something. And they are trying to follow individual axons. And so, indeed, they are at the level of trying to have, individual pixels represent cellular structure. But at some point, they want to be able to back out and look at the non-local kind of behavior. That's going to be very, very challenging. But so, in other words, we're not that far away from needing to answer that question.
Database
at
both scales.
Yeah, that's right.
But right now, there's no
exactly. That's right. So I have a group in Waterloo who's working on the coarse scale. There's a Center for Theoretical Neuroscience, and they do super high scale kind of neural modeling. But then these other people doing like these amazingly fine scale sort of neural reconstructions, but there's a big, big gap in between. So I don't have much insight right now, but it's totally worth working on. So yeah, great question.
You said that you could potentially reduce the number of filters by a factor of 3.
Like in the previous slide here, yeah.
Did you ever play with training on much less data then? Because
yes. Oh yeah, that's right. Yes, we've also looked at sort of the robustness or the basically the robustness or the trainability or the degree of overfitting as a function of the amount of training data. Yes, we have sort of results like that. I don't have those here. But that is clearly the relevant next question because that's what I said is that I don't want to have 50 million training images. So obviously then, okay, can you do it with less? And there are sort of, in deep learning, there are metrics for overfitting. I can't remember off the top of my head exactly what the terminology is, but there are things that people look like as telltale signs that you're getting there. And so those are the kinds of metrics that we're using to try to understand where are we at in terms of learning, overfitting, underfitting, not learning well enough, et cetera, as a function of degrees of freedom and training data. So yeah, that is what we're looking at.
I have one question. I'll take the other one offline, actually.
Sure.
The slide that came right before this one.
Yep.
Now you're talking about, what roughly 75%.
In this particular application, but yes, yeah.
75% recognition rate. So when you're talking about 300 learned filters, so what are we learning exactly? The parameters of the filters?
Yes.
What are we using? At the end of the day, what am I using to actually do the recognition?
At the end of the day, the actual recognition is done by like a support vector machine on some output layer. Not on the parameters of filters. So basically, you have filters. You might have multiple layers. I don't even know how many layers we had here exactly. But you've got filters over multiple layers. And then you have a fully connected layer at the end, which produces a bunch of outputs. And these outputs could either be your classifier directly, in that the maximum value of all these outputs is my decision, or it's a feature vector that I feed in support vector machine. You can do either one. I don't actually, off the top of my head, remember exactly which one this is. But when the student talks about filters, what she means here is these actual convolutional kernels. And I can just keep offering that network more. You want another filter? Here, have another one, right? And so as you increase the number of filters, so these are like the kind of structures that you're seeing in your work, local, like Gabor-like things and lines and edges and blobs and stuff, that kind of stuff. That's what these filters are.
In other words, I'm having trouble kind of assessing.
Oh, what's a lot and what's not? Yeah. No, this is not 50 million training samples. So this is a greatly reduced problem. So 300 filters is not crazy lot, and there's also not a huge number of layers here. So we're working on definitely a much smaller problem. But we're motivated by like these Netflix, kinds of problems and, images in the wild and stuff like that, where you have these really tough kinds of learning problems, but probably never enough data. Right? Well, I suppose, but it's large relative to what? So images in the wild is a very big data set, but it's maybe not big enough to actually reliably train a deep network to achieve the kinds of recognition rates that you want. So if you can have a constrained network that can take images in the wild and actually get higher performance, that would be great. So that's the kind of questions that we're trying to explore here.
75% sort of the state of the art?
Good. Well, that's a good question. So yes and no. So it's terribly difficult to reach state of the art without an awful lot of tweaking. So they have little knobs that they turn for like this kind of learning and this kind of momentum and this kind of like repeated randomization, and like there's a million things they do in order to get the training rate like just up to the state of the art. So I'm not interested in doing all of that. So I would rather just take a regular network and then just see if I take this kind of strategy on constraining the network, if I take this kind of strategy on feeding in scale-dependent stuff, how does the trainability and how do the degrees of freedom change? And so presumably, if I see a positive change, if I then were to tweak it endlessly, I would see a positive change. Ideally, of course, at some point, we're going to need to try to do a more optimized network to show that the changes we see here also translate into the state of the art. But I would rather not do that for most of the research process because I'm interested in principles, not in competing with what some group did with endless sort of parameter tuning. That's the presumption, and so for now, I think that's okay. At some point, we do need to demonstrate that we're not guessing, right?
Now, let's thank our speaker again.
All right, thank you. Yeah.